Welcome to my channel. Today let us learn NAND gate analysis. At the end of the video, you will get the clear picture of the design and the schematic of the NAND gate and how to do the transient analysis and what are the uses of doing the transient analysis. Like you can find the TR, TF, propagation delay and Fmax and to verify your truth table practically. And basically, the NAND gate stands for NOT plus AND. At the input side, we'll perform this AND operation and we'll invert it at the output or we'll invert the result. So, knowing the truth table of a NAND gate, if both the inputs are high, our output will be low. And for all other combinations like 00, 10, and 01, our output will be high. And we know the Boolean expression of a NAND gate, that is y is equal to a into b whole bar, which means the two pmoses will be parallel to each other and the nmos will be series to each other. Then why do we study this transient analysis? Basically, it helps us to know whether the gate is working correctly or no, and to verify the truth table practically, and to know T rise, T fall, propagation delay, and maximum operating frequency. So this is the design of an AND gate where the two PMOSs are parallel to each other and the body of that is connected to the higher voltage, that is VDD, and the two NMOSs are connected in the series and the body is connected to the lower voltage, that is VSS. And this is a symbolic schematic of an AND gate where the two inputs are given here. This is V1 pulse and this is a V2 pulse, which is ranging from 0 to 1.8 volts. And this is a VDC, which is of 1.8 volt. And at the output, we have connected a capacitor, which is of 100 femtofarad. And this is the waveform at the end of the transient analysis you'll be seeing. And you can find TR, TF, Fmax, and TP by knowing this waveform. The schematic of a NAND gate analysis. As per the Boolean expression of a NAND gate, y is equal to a into whole bar, we place these two PMOSs in the parallel and the NMOSs in the series. And we always make sure that the PMOS body will be connected to the high voltage, that is VDD. And in case of an NMOS, it will be connected to the lower voltage, that is VSS. And we have given an pin for the A and we have label for the B and we have label for the A and we have given pin for the B. And VDD is connected, VSS is connected and Vout is connected using the pin. So once the schematic is done, we'll move into the creation of the symbol. If you want to know how to create the symbol of this NAND inverter, just you refer to the previous CMOS inverter video. So this is the NAND inverter symbol. We are going to provide the V1 pulse and V2 pulse and this is a VDC and this is the load across the output. So we'll just check and save it. We'll go to the launch window, ADEL, and we press on this. As even in case of an NAND inverter, NOR inverter, and even in case of an XNOR, we just do the trans analysis. So just click on this trans and stop time in case of trans is 100 nanoseconds, and we just click on this moderate and say apply. Okay. Then to plot it, we'll go to outputs to be plotted, select on schematic. So inputs A and input B, and we'll select on this output and again go to this window, just run it. So if you click on this, you'll get A, B, and this is the V out. Once we get this waveforms, just we need to click on this output, then go to send to calculator, then just copy this, then you clear the buffer, then function, then find this rise time, then click on this rise time and you paste here and always make sure that the initial value is 0 and the final value is 1.8 and for rise time the percentage low is 10 and percentage high is 90. Then you click on this apply, then OK, then this append, you'll find the value of rise time, that is 2.351 into 10 to the power minus 9, that is 2.35 nanoseconds. You can see here in the aerial window where the rise time is updated. If you want to find the fall time, again we will go back to our waveform. We'll right click on the output waveform, send to calculator again, then you copy this, go to clear buffer, then to the function and you type the fall time, So once you find the fall time, you just copy this back, and always make sure that the percentage low is 90 and percentage high is 10 for the fall time. And we'll say apply. So once you apply it, then you say OK, then go to append. Then you can see here on the window the fall time is updated. Now we'll again click on the append, and so that it will come on the aerial window. Now see here, both rise time and fall time is updated. Now we right click on this rise time, edit it, and say the name TR, and we'll say apply, then OK. Then we again right click on this tfall, then we'll give it as TF, and we'll say apply, then OK. So now you can see the names have been changed, TR and TF. Then we'll calculate the F max and TP for it. So again we'll right click on this and we'll say edit, and we'll change the name of this TR to F max, and we'll also change the formula. We'll change the formula to 1 divided by TR plus TF. TR plus TF, and then we'll say add it, then apply, then OK. Then you can see here the F max is not updated, so that you have to run it. So once you run it, you will see back the F max in the aerial window. See here, some value of F max is updated. Next we'll click on the edit option, then we'll go to the window again, and we'll change it to TP, that is propagation delay, and then we are going to change this formula to 0.35 into open bracket TR plus TP. Then you make sure that you close the bracket now, and we'll say add it, then we'll say add it, and then we'll apply it, then click on OK. Then now we'll run it. So once you run it, you can see on the aerial window that the TP is updated. So this was all about the transient analysis of the NAND gate. Thank you so much.